Thank you, Dr. Nick. Welcome, everybody. Good afternoon. My name is Lennon Ganz. I'm from Santa Barbara City College, majoring in computer science. This summer I was working on finding patterns in complex social networks. I was working with my mentor, Dr. Ingli Wu, back there, my faculty advisor, Dr. Jifeng Yan, from the computer science department here, and we're funded by the National Science Foundation. Okay, so what is a social network? Well, in general terms, it's just a network of social interactions. Okay, so here we have a small example. These are three of my friends. We have Zach, Shane, and Danny. They're connected by certain relationships. Zach is friends with Shane. Shane is friends with Danny. Zach is the classmate of Danny's. And this would be an example of what we might call a simple social network in the form here of a simple social graph. Okay, and the term simple here meaning there's only one type of entity represented. It's usually people, in this case it is. But if we were to, and each one of these can also have a set of properties associated with it. If we were to add something to this network that wasn't a person, it would then become a complex social graph that contains multiple types of entities, not necessarily limited to people, but you could also have places or events or institutions if Danny was a student at UCSB. And this introduces a number of challenges actually, because networks can get very large, very complex, very quickly, and if you want to get some information from the network, it can be difficult to ask a system a question that it understands what information you're looking for. The questions here, they're called queries, but they can be very difficult to write. So my objective for this summer has been to design a simple, intuitive platform for analyzing these complex networks. And the data set that I've been using is actually the Global Terrorism Database, which is available publicly online. But so I'm using this data set as the first set of data to basically test my system. As far as the process of designing a graph analysis platform, first we have to understand what's already out there so that we're not doing anything that other people already have down perfectly. There's no reason to do that. Neo4j and Titan are two examples of existing graph databases. We first look at what they do well and how they can be improved. Next, we need to identify suitable queries and algorithms for social graphs. The query being a question that we have of the network, and the algorithm being a set of instructions that the system does to answer your question. And we also want to propose and research optimization techniques both for the asking of the questions to make it intuitive and user-friendly, to be able to ask the question that you want, and also for speeding up the algorithms, making them quicker and more efficient. So what types of questions might we be interested in asking? Well, for this specific data set that I was working with, we have three main types of queries. Okay, the first type we're going to call they're aggregation queries, which is a simple type. You're just basically asking for information that's directly there in the data. Doesn't really have anything to do with how the data is connected. A couple examples: how many attacks were there in 2005? What was the most common type of weapon used? Okay, this doesn't use the power of graphs at all. It's just looking directly at the data and not the relationships. Reachability queries. These types of queries you're asking, are two different parts of the network connected in some way through some path within the network? For example, have these two terrorist groups ever collaborated on an attack? And last but not least, we have actual pattern matching, where essentially you're looking for a small graph within a larger graph. You're looking for a pattern of nodes and edges within a much larger graph. And this example is supposed to be kind of complicated. We have another example later on. You might be interested in finding instances where a terrorist group targeted a government official who had also been attacked by a different group earlier that year. Now, let's say we have a query. We want to get some information from about the network. This is us up here with the user. We have our question, we work through a graphical user interface in order to formulate the question, and then it gets parsed or translated into something that the system understands exactly what we're looking for. It goes down into this query execution engine, which is where the algorithms are. This is where the results are compiled and then sent up back through here and back to the user. The algorithms have to communicate back and forth with your graph files down here, which is where the actual data is. And speaking of data, we actually need to start with some data and build up the graph is the first step before we can do anything else, before we can learn from it. So using the global terrorism data, we have to design a converter that will convert the data from a spreadsheet, which is the form in which it starts out, which is not very useful for seeing relationships between the data, and convert that into a graph. So what the converter does that we designed was go row by row and cell by cell in the spreadsheet, reading the data, adding this data to either a new part of the graph, if it deserves its own a new part, or some existing node in the graph. And then last, we have to connect the data by appropriate edges, depending on what we're reading in. And this is automated. It automatically goes through the entire set of data and builds a graph. And after we have our graph, this is just a visualization of a small part of the database. I loaded it into some existing graph visualization software. It's called Gephi. But this is just to give you a visual sense of kind of what the data looks like. And you can already see parts of the graph are a little bit more dense than others, indicating potentially more activity around certain groups or certain incidents or something. So say we want to actually answer some questions that we have now. And we'll step inside our query execution engine, and one of the types of queries that I mentioned were reachability queries. Again, this is where you're looking at trying to determine whether a couple parts of a network are connected by some path. One method, one algorithm we use to do this is called a breadth-first search. We have a start node and an end node, and we're looking to find a path between the two. We start at the start node and explore all the nodes that are directly connected to it. And this is, you take a step, it's called. So now we're one step away, we have its neighborhood. We do this again for those nodes, we step again, until we either run out of nodes to check or we run into the node that we're looking for. We can see in this example that there is indeed a path between the start and the end, the path went before. You can see that down here, these four nodes are not connected to any of these nodes, so there would never be a path if we were interested in the node there. There would never be a path between those. But one way we can actually optimize this process is, instead of just starting at the start node and working our way towards the end, we can start from both at the same time and try to meet somewhere in between the two. So instead of just radiating outwards from the start until finally you reach the goal, you do both at the same time, and it saves quite a bit of time. How much time? It's almost always faster than a normal search. In rare cases, it would be the same speed. It's tempting to think maybe it's twice as fast, since you might be meeting in the middle. Maybe 4 times as fast, has something to do with the area. But what we found, we ran a couple different tests. This is one of them, where we increased the size of the graph, changing the number of nodes, and the performance increase for this bidirectional search. It looks almost linear. It's not quite. It's curving off here. But you can see it quickly goes up to 30 times faster, and it's still increasing as we're increasing the size of the graph. On the other hand, if you keep the number of nodes constant and increase the probability that any two nodes are connected by an edge, you're essentially increasing the density of the graph. The trend is that the performance improvement is great around here, where it's not as dense. As you get more dense, you approach it's sort of an asymptotic trend at 1, which would indicate that they're the same speed. But this is what we explored with the reachability queries. The next thing that we did was pattern matching. I provided a somewhat complicated example before. This is another example of a pattern that we might be interested in finding in our network. We might want to search for 2 distinct incidents that had the same perpetrator and the same target. And you'll notice that this is a graph. It's a small graph, and we're looking for this within a larger graph. This is another visualization of the network. So what our algorithm for this does is, I can't go into too much detail for the sake of time, but basically tries to find this graph somewhere within here. If it does find it, it will return the pattern that it found. This is just an example of that particular pattern that I ran on a subset of the graph. And it can return you some information about the incidents, the name of the perpetrator group, the name of the target. But this is really, this was the exciting part of my research, because I got to a point where what you could learn from the network wasn't limited by trying to make the tools, but it was limited instead by what you can think to look for within the network. You can come up with any number of patterns, an infinite number of patterns that you might be interested in finding. And that was pretty exciting for me to get to that point. Now, as far as what we've done and what we still have to do this summer or in the future, we have some ongoing development. We are still working on our graphical user interface, which will allow us to design those certain types of patterns that we're interested in. Anything you can think of, be able to search for those. And then the interface will also provide a clear view, a visual of the results of those queries. We're also looking to have some geographic visualization of the results, because a lot of the data that we're interested in has to do with places on a map or on the globe. So it would be nice to be able to see those actually on a graph, or on a map or on the globe. And then we also we want to allow other developers to import their own data sets, use our system to analyze any type of data that they would like. So we're developing an API, an application programming interface, to allow just that, so that people can use our system for their own sets of data. And that's what I have for today. Thank you for your attention.